Okay, so if we start, so we'll start with this zip file here. If we open it and extract all the files inside to any folder of our choice, but it's important to keep the folder in the mind because that's the folder we'll need to open in Matlab. So as you can see here, the folder is on desktop called tutorial. So once I have Matlab opened, let's see. Okay, so once we have Matlab open, we can go to this folder here where we extracted our file. So here it's desktop and then tutorial. So we go to the desktop and then find the folder called tutorial. Then we should be able to see the files here. It's very important that we are exactly in the same folder. Desktop tutorial on the top, we can see here. All we need to do is we need to click on this file called asp.quadcopter.prj. It's a project file. Just click on it and Matlab will open by itself. The simulation environment will open by itself. It takes a bit of time, maybe 30 seconds, 40 seconds. It depends on the computer. So if you have a good computer, it might take even less. So in my case, you can see it took about 30 seconds and we will have more windows popping up. Will not be clicking on anything, and then yeah. So as you can see, if you go to the Matlab, if we look at the workspace on the right, we have all these variables which have been initialized without us doing anything. So these are all different variables and that are required for the simulation to run. And once the simulation runs, this is where we will find our states, recorded data, and everything else. So at this point we'll minimize it. We will come to this window here on Simulink. So I have basically modified the original project files, and the reason is because normally we have our desired trajectories in this block here called command, but when we try to run hardware tests, only this blue block is uploaded to the actual hardware. So we cannot run hardware test without the trajectory. So what I've done is I have added the trajectory inside here. So for our case, we don't need to focus on the brown blocks because these have been made by the OEM, and they're basically only for the simulation. The brown blocks that you can see here, they're only for the simulation, because only the blue block is uploaded to the flight computer. Yeah, to the UAV. So these are dynamic sensors which have been modeled in Simulink. So you can see here. Environment, you have the nonlinear or the linear airframe. It depends on what we choose. So VSS vehicle, if it's set to 0, we'll select the linear airframe. VSS vehicle, if it's set as 1, we'll select a non-linear airframe for testing. So again, where we can set these variables is here. If you can see, VSS vehicle is set as 1, so that's a non-linear airframe. We can change it. For example, there are some variables here in the tasks file. Estimator variables, controller variables, these can all be changed. A trajectory tool, but vehicle variables is an important file. It has all the gains and other, for example, here is the vehicle airframe mass, and this is the inertia from the vehicle. We can call for in case of Mambo, which what we're using, in case of Rolling Spider, which is another drone, but that's not applicable to us. But these are the values for the drone. And then we also have the rotor dynamics and everything else here, the motor limits, minimum and maximum, and the other gains. These are to gains are to calculate the thrust and stuff like that. We don't need to modify any of those for now. For now, all we need to do is we need to focus on the Simulink window here. And for our ease, I have changed the colors of the blocks that we're interested in. So as you can see, we will completely ignore the brown blocks. We'll only click on the blue block, nothing else. So once we click, we see two further blocks. And the bottom one, as you can see, is the image processing system. We're not using the camera as a guidance tool here because we're only interested in the study of control systems. We can later on use the image data from the drone to correct our trajectory or improve our performance, but at the moment we're just using purely controllers and the other sensors. So once we click on that block again, we can see we're in the flight control system block now. So there are two blue blocks. Again, we will ignore the rest of the blocks for the moment. So I can go through them if you want quickly. So this is collecting the sensor data. We use the accelerometer, gyroscope, ultrasound, pressure difference, and the battery data to log them in this sensor data group. And we use that sensor data in the estimator. There's a bunch of Kalman filters which are built in here by the OEM and a complementary filter. So for example, altitude estimator, and then we have the XY position estimator, and other things is going on here. We have sensor pre-processing, we have the sensor biases and everything else here. It's all been done by the OEM, so we don't need to worry about that. We can change the flags. So for example here, if the difference between the measured position and the actual position, the desired position and the measured position is greater than 10 meters, it'll shut down the drone. Similarly here, it's greater than 6 if the desired dx and the actual dx is the difference is greater than 6, it'll shut down the drone. So we have all these flags that we can program. So if you're in a small room, we can make this into let's say 1 meter deviation from the desired trajectory, it'll shut down the drone. Or if you're in a big open field, you can make it even bigger. Yeah, so we got the sensor group covered, we got the estimators, we got the crash predictors, and this block is just, it's taking all the values and logging it into some variables for us to analyze them later on. So again, for our purposes, we're only interested in the blue blocks. So this block here generates the reference value commands. I've named it landing logic. You can maybe name it to reference signals or something else. It will not change anything. But let's go into it and have a look here. So here you can see X, Y, Z and roll pitch yaw. These are our desired reference trajectories. So for example here I've set everything else as 0 except the altitude. So right now I'm telling it to hover at 1 meters, which is what will happen. So you can change that. Let's say you want it at for some reason you want it closer to the ground, so we can set it at 0.7, so it'll just hover at 0.7 meters. If you want to change the positions, you can also change, let's say you want a sinusoidal trajectory, you want the UAV to hover in a circle later on, we can select that. We can just delete the X and Y and then just drag it here, right click and drag, just copy it, and then we can change it. So for example at the frequency of 1 radian per second, and change the amplitude, and whatever we want we can just do it. But I'm just gonna leave it here for now and set it to 0 just for a simple hover test. In this case we can also select other types of trajectories, or maybe we can create a switch where it's constant or 0 for the first 10 seconds and then goes sinusoidal later on. So it's all up to you. You can change what this is where you generate the trajectory, and this trajectory will be uploaded to the quadcopter. So yeah, we can generate any trajectory here, but we'll prefer X, Y, Z, and yaw only. We just leave the roll and pitch as it is for now, because we generally want roll and pitch to be 0 unless we are maneuvering somewhere. Which in our case it'll be automatically calculated, which I'll go on about a bit later, like how that is done and stuff. So going back, so this block handles our desired trajectory. Again, I have modified the simulation files, so we don't need to do a lot of tinkering. We just leave these variables alone for now. So we just select roll desired X, desired Y, desired Z, and desired yaw. We can select our own generated trajectory using these blocks, or we can use some other functions that whatever we are free to use whatever we want. So going back now, the only block left to discuss is now the controller, which is the main block that we want to look at. So if we double click on that again, open it again, so we'll see there are a few sub-controllers, let's say. So if we see the yaw controller here, it just controls the yaw. It's a simple PD controller. We can change the gain values and have a look at its performance, how it affects the performance and stuff. Again, if we look at the altitude controller now, again a PD controller for altitude, and they have also incorporated another signal which is added to the controller output, and this is to account for the mass of the quadcopter. So the PD controller action only handles the changes in the altitude. So let's say if I wanted to hover at 7 or 1 meter in our case, let's say I wanted to hover at 1 meter, and then after some time I wanted it to go up to 1.5 meter. That's where the PD controller will kick in, and this part will just handle the mass of the quadcopter, because the quadcopter has some mass, and then it I mean, this is how the inbuilt controller has been designed. We can obviously take this off and then use a simple PID controller to handle the whole thing, but it's completely up to us how we design the controller. So these red lines, you can see we can edit it out. So we can take the state estimators from here. This is the estimated state, and then this is the desired altitude. And we can feed that error into any other different controller, for example, let's say sliding mode controller or some other controller that we like. This is a saturation block. It's better to leave it as it is, because it has some control limits, which are inbuilt limits. So once our control signal, let's say U1 for altitude, we'll just plug it in here. We'll delete these parts, and we'll just plug it in here, and we'll make sure the saturations are as they are. So this is for the protection of the drone. If we delete the saturations, it might result into unstable behavior, and it might damage the hardware as well. So coming to the complicated part now. So for this controller specifically, it's called a PID cascaded control. So they use PD controllers to take the desired position, X and Y desired positions, and if we go look inside, we have two PD controllers. The first one with, let's say, PD controller for the X position is, this is the gain, proportional gain. For the Y controller, this is the proportion gain, and similarly this is the derivative gain for X, and this is the derivative gain for Y. So what this does is it controls the desired position into desired pitch and roll signal. So because we know the position is related, position of a quadcopter is related to its pitch and roll, because that's how a quadcopter changes its position, by the manipulation of pitch and roll commands. So this pitch and roll command is then forwarded to the pitch and roll controller over here. This switch is there in case we want to directly control the pitch and roll. In that case, this command will not be forwarded. Instead, the direct reference signals from the trajectory blocks will be forwarded, if that's what we are interested in. But that's rarely the case, since we don't directly control pitch and roll. We use the position X and Y to generate some desired pitch and roll commands, and then we design a controller to attain those pitch and roll values. So as you can see here, we have a PID controller with again, we have pitch and roll, pitch rate and roll rate. This is the proportional gain for the pitch and roll controllers, integral and derivative gains, and this is the anti-wind-up. For example, this is the anti-wind-up gain, this is the anti-wind-up setup, to prevent the wind-up of the integral action. So yeah, these are then signals, tau pitch and tau roll, which are fed to the motor mixing algorithm, and this is passed on to the motors. And these green blocks, we don't need to worry about them because they have already been set up. So again, I will highlight it that I've changed these these files, so we only need to worry about the blocks in the light blue color. And we can see here, if we want to run the simulation, there's a scope block that I've set up. It allows us to view all the states. So let's say if we want to run the simulation, let's have a look at our desired trajectory for now. So let's say we want our quadcopter to hover at 1 meters, and we select the positions as 0, 0 for the case of simplicity here. If we there's two ways to run the simulation. We can either click this button on top, run button, or we can also click the play button here. Both are effectively the same buttons, but let's click here run button, and then we will see the simulation, and then we will also see the live graphs. So as you can see on the bottom, it's saying compiling. It might take a few minutes to run the simulation, and then we will see the real-time plots also. Yeah, the simulation is about to run. This is just the bottom camera. This is the simulated view of the camera, what the quadcopter sees at the bottom. We can just minimize that, and we can just see, you might be noticing that the altitude is not visible. It is visible, but it's not on the correct scale, so we need to press this button here, and we can see the altitude is at 1 meter. The other values, even though they were set to 0, are not strictly 0. This could be because of the noise in the estimator, or signal sensor noise, or something else. But you can see the magnitude is very small. Is 10 to the raised power minus 4. Yeah, so same with the yaw. If you keep looking here, we see the dynamic simulation. You can see the time, and the simulation will terminate at 30 seconds. We can change that time obviously by changing this t final. So if we expand the image, we can see the altitude here is as our desired altitude we had set to 1 meter. And then the position y, even though we had set it to 0, we can see there's some, it could be because of the rotor effects or some other dynamic effects that we have not taken into consideration. But it's the magnitude, as can be seen, is 10 raised by minus 3, so it's quite small. And yeah, that was the simulation, and we can also try to run the same simulation on the hardware by deploying this exact controller. This exact controller can directly be deployed on the hardware, and then we can test it to compare the simulation and the hardware flight test results.